So today, the important thing to study is the material mechanical properties are called. So basically, we will start studying concepts like stresses, strains, Young modulus, Poisson's ratio. We are going to study very briefly what is ductility, what is when a material is brittle, what is elasticity, the distinction between these two very different behaviors um, in terms of mechanical forces. So in the first place, remember that in structures, it's very important to take into consideration the units you use. So it's important to recap a little bit and to be sure that we understand that the forces are in our context, because we use the international system of units. The forces are measured in kilonewtons, usually in our exercises, but you can use newtons as well in some applications when the loads are smaller. The displacements are usually expressed in millimeters or meters in our problems, as you know. The stresses will be forces applied over an area, so they will be measured in kilonewtons per square meters. But there are other units for stresses that are usually used. For example, pascals or kilopascal or gigapascals. And these units are used as well for pressure, because a pressure is a particular type of stress. We will not discuss the difference today, and the other thing that we need to consider in our structure is the strains. The strains will be defined after in the second semester in a more accurate way, but basically is a measure in percentage, or sometimes we say it's a dimensional, because it's the relationship between the deformation over the original length of our structures. So what is a Pascal to understand? A Pascal is, again, is a unit of stress, and this is why 1 Pascal is equivalent to 1 Newton per square meter, and then 1 kilopascal will be 1 kilonewton per square meter, and 1 gigapascal will be 1 kilonewton per square millimeters. Because the values, the size of these numbers we use is better to be expressed in our structures and in our context in kilonewton per square millimeters instead of kilonewton per square meters. So 1 kilopascal will be 1,000 pascals, then 1 megapascal will be 1,000 kilopascals, or 1 million pascals. And 1 gigapascal is the unit we usually are going to use for Young modulus, especially for steel, is equal to 1,000 million of pascals. So try to play with these units to be sure that you understand the equivalences, because not to be confused when you resolve the exercises. More equivalences in there, you can study by your own. So today, the focus is a particular test we run for steel. You will study in materials and geology. So you have a lab experiments that the technician will show you in every single details, in reality, how this works, how this curve you can see on the screen is produced by a machine. But basically, this test is the simplest test you can do on steel. So you have a sample of steel and you pull with a force P. This will produce certain stresses, and this will produce certain deformation that will be translated to strains. So the machines there give you directly the stresses and the strains. In the past, for example, you had machine that gave you forces versus displacement, and you had to transform these two stresses and strains. But the shape of the curve is always the same. So in this case, we have the response of the sample of steel when you apply forces and you increase the forces little by little. So you see basically the mechanical behavior, the mechanical response of this sample when you apply uniaxial forces. They are called uniaxials because they act only along one axis, the vertical axis in this case. And you have as a reference the initial length, because the initial length is what you need to calculate the strains, basically. So every increment in the formation divided by the original length, this should be L0, is going to give you the strain. So the deformation in percentage, basically. So it's important to understand exactly what these curves mean in terms of, of behavior of your material, the steel in this case, because then steel is a material that we use a lot in civil engineering. So remember, the important thing is that this is a very, very simple test. So you are just pulling a bar, because as you can imagine, you can run other tests, compressing the bar, applying bending moment to the bars, for example, putting the bar in a horizontal direction and applying vertical forces to see the behavior as a beam. But in this case, it's the simplest one. So we are just pulling, we are just doing a tensile test on this sample of steel. But it's very interesting to see the behavior from the beginning, when you don't have any load, until you have a load that breaks the material, and to understand exactly what all this curve mean, little by little. So in the first place, we have for every sample of steel we test, if the experiment is well set up, we will see the first region we call the elastic region. So basically in this region, from the time that there is no load of P is equal to 0 until P has certain value, in all this region, the material behaves following what we know as the Hooke's law. The Hooke's law is the law for linear elasticity. It's the simplest law for linear elasticity in this case. So the material behaves linearly, we say, because the representation in this space of stresses and strains is basically a straight line. And because the expression that gives us this line mathematically is sigma, which is the stress, is equal to a constant called E multiplied by epsilon. Epsilon represents the strain. So this expression, this mathematical expression, is telling you that there is a proportionality between the stresses and the strains. And this proportionality is constant, is a material parameter, we say, and this is called Young's modulus. And this is a very important modulus for us to know when we deal with materials in civil engineering. But there are certain characteristics that I have mentioned already, and they are important. So this Young modulus is constant for the material. And this is the reason why this expression is linear, because there is no any power in these variables. So this is your independent variable in this space, and this is the dependent variable, the stress. So for every strain, you will have a value of stress multiplying the strain by the Young modulus, which is a constant. So the other characteristic that is very important in this region of the test for this material is that all the formation are recoverable after removing loads. So if you increase the load until the middle of this green line in here and you unload the sample, you will recover all the deformations. And this is why we say this material is elastic in this region. For these values of loads, you can apply from 0 to this value of sigma p in here we will define out right now. So again, in here you have the definition that the stress is directly proportional to the strain. E is the Young modulus, and the Young modulus is important to remember as well, have unit of stresses, because remember that the epsilon or the strains are adimensional. So in order to get stresses, you need unit of stresses for the Young modulus as well. And the point one, the limits where we define this first region, this elastic region where everything is linear, is called the limit of proportionality. And this is why I call it in here sigma p. P is for proportionality. So this means that from 0 to 1, we have a linear elastic behavior. After the point 1, this behavior is not going to be the same. It's going to be a little bit more complex. And for example, if we study the behavior from 1 to 2, in this curve we have recovered from a test in the lab, we will see that, we will see in more details, this region from 1 to 2 is not linear anymore. It's a little bit curved, so we cannot apply the same expression, a linear expression. So in this case, the stress is not going to be proportional to the strain anymore. There will be some sort of different expression in here with epsilon to the square, for example, or to 1.5 or something like this, that will represent the nonlinear behavior between 1 and 2. So in this case, however, the material still behaves as an elastic material, because if you load until this limit 2 in here and you unload the structure, even when it's not linear, the behavior of the material will be that will recover all the deformation and will go back to this 0 in here. So this second point is called the elastic limit, because if you load your bar until this limit, you will recover all the deformations, something that won't happen after this 0.2 in here. So from the region 2 and upwards, so from 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to the point where you break the structure, all of this is called the plastic behavior, because it's not linear anymore, evidently, because you can see that there is a curve from 2 to 3, another curve from 3 to 4, another from 4 to 5, etc., and etc. So you don't have an elastic behavior anymore after the 0.2. This behavior, which is different to the elastic behavior, is called plastic behavior. So just doing a recapping here, because things are becoming complicated. From 0 to 1, we have elastic behavior, but not only elastic, but linear. From 1 to 2, you have elastic behavior, but it's an elastic non-linear behavior. And from 2 to the end of the curve, you have a plastic behavior, which is non-linear. So after the 0.2, at every point, if you remove the loads, you will have permanent deformations, and we will see in more detail how this works in a previous slide, in a subsequent slide. But for now, remember, from 0 to 1, linear elastic behavior. From 1 to 2, non-linear elastic behavior. So from 0 to 2, you have an elastic region. From 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to the break, you have a non-linear behavior, which is additionally a plastic behavior, because you have permanent deformations. So if we want to, again, to show clearly these two different regions, you have the elastic region from 0 to 2, where you recover all the deformations that could be linear or unlinear or non-linear. And you have the plastic region where everything is non-linear and you don't recover all the deformations of your bar. As you see, even with this simple test, pulling the bar in an with an uniaxial force, a lot of things happening in the material in terms of mechanical behavior. So you have a region where everything is elastic and everything is linear, another where something is not linear but still elastic, and other region where the behavior is plastic and you cannot recover the deformation. But we can study in even more details this curve from the 0.2. So let's say in this region from 2 to 4. So you will reach this peak at the 0.3, and this peak is basically what we know as a yield limit, or yield. Yes, the yield limit is called. So this is the maximum value. I should add in here in this graph. when that indicate that the plastification of the material have started. The plastification is precisely something that internally happen with the atoms and molecule of this metal and produce this behavior, which is totally different to the elastic behavior. So in this region, you can see that even reducing the value of the stress, you have deformations, because in the horizontal direction, you are measuring deformations. In the vertical direction, you are measuring stresses. So it's weird that, you know, until the point 3, in order to get deformation, you needed to add stresses or to add loads. But after the point 3, there is something happening internally in the composition of this material that produce this behavior that with less stresses, you have more deformation. This is because the plastification has started. So let's say that the material loses its strength and start behaving in a different way. In the region from 4 to 5, there is a region that is almost horizontal. So in this region, with no changes in stresses, no changes in loads, you still have deformation. So you still have a process of plastification. So this is typically a behavior from a ductile material. So it's not for every metal. So a ductile material is precisely ductile because present this behavior until certain point 5 where something happened internally in the molecules and internal, you know, atoms of the material, and we will see what's happened exactly. So in this region from 5 to 6, you see that there is a kind of recovery. So the material start behaving again as a, let's say, a standard material. So you increase the stresses and you increase the deformation. So in some way, you can say that the material have recovered its strength, because in this region from 2 to 5, something happened that the material has changed in the way it is behaving from the beginning, but it's not broken. And because this plastification process in here, because the stresses you have reached in this region of the curve, you have recovered the strength and the material is again even more stronger than before. And you reach this peak at the point 6, that is called the ultimate stress, because this is the maximum stress you will find the material is able to take before breaking. Because this recovery here is have this shape basically, so you have this curve that have this slope, positive slope, and increase in values in terms of the stresses when you increase the deformation. We call this this region or this behavior as a hardening. Hardening means that you are having a material that is stronger and stronger after a plastification process. From 6 to the point where the material break, you see that the behavior is exactly the opposite. So you are declining the strength of your material until you break at this point, at the end of this curve. And this is called softening in when you are talking about material behavior, mechanical behavior, because it's exactly the opposite of this other curve from 5 to 6. Another characteristic or another thing that is very interesting to see in the lab when you are studying this material under, you know, this sample under uniaxial tensile loads, is that at this point you notice in your sample that there is a neck produced in here, and this is again for ductile materials. So this neck is telling you that the material was plastified already, so it's behaving in a way that is not elastic at all. And of course, this curve will capture the differences in this cross-sectional area. And because the stresses are forces divided by the areas, of course, the stress will be affected by this production of this necking here. And this is the reason why you have this behavior of this curve in this way, because actually this curve is representing not the actual stress of the bar, but the stress that is affected by this production of this neck and this reduction of the actual cross section. So a lot of things are going on in this simple experiment, but let's see in more details what happens with the loading and unloading, because this is a situation that is very common in civil engineering. You not only have the structures that are being loaded, but you have a structure that are being unloaded as well all the time, because in reality these forces are not permanent. So if we compare with the exercises we do in this module, the exercises we do are with permanent forces, but in reality you have loading and unloading. So if you are in this elastic region and you load your structure, in this case your bar at the lab, what you will see, and let me just check that exactly. What you see is from 0 to 1, for example, you will load until the middle in here. When you unload, you will go back to the origin of coordinate 0 again with no any permanent deformation. If you go with your load until the point 1 and you unload, you will recover again all the deformation. You will be following this path, this only path, which is linear, and you will go back when you have no load to the point 0 again, no loads, no deformations. And from 0 to 1, the law or the mathematical expression that represents this behavior is simply sigma stress is equal to Young modulus E multiplied by the strength epsilon. From 1 to 2, again, let's say you load your bar until the point in the middle in between 1 and 2, and you unload, you will follow this path, non-linear, this small portion in here, and linear from here to here, and you will recover the original deformation you had in your bar. So no permanent reformation at all. Same thing if you load your bar until the point 2, because you are exactly before the limit of elasticity. You will unload your bar and you will recover all the deformation and you will go back to the origin of coordinates in here. But from 1 to 2, you cannot apply anymore the proportionality. You cannot apply this simple equation, sigma equal to E times epsilon. The expression will be different. I'm not putting any expression in here because there is no one expression. There are several expressions depending on the material, and we cannot cover these more complicated situations or materials in this module, but definitely won't be the expression sigma equal to E multiplied by epsilon. Will be something different. But the recovery is total, so you don't have any permanent deformation. This is the important thing to remember and to distinguish. If you are going farther to the point 2, the limit of elasticity, what happened? Let's say you load your bar, your tensile sample, you reach the point 2 and you go farther to the point 3, you notice that there is this curve in here and you reach this point here just before the point 4. And after that you decide, okay, let's see what happens if I unload this material. If I unload this material for that point, the unloading is not going to follow the path in blue because it's not elastic anymore. We'll follow a path that is this path in green in here, this second line in green. Sorry for that. So, and this path that the material is going to follow in the unload process will be parallel to the original elastic path you had at the beginning of the experiment. So the Young modulus in this new elastic area will be exactly the same, because the Young modulus is a material property. It's not going to change in the region of elasticity because this is part of the material itself. So even when you have producing here a process of mechanical changes in the way that internally the material works, the elastic region remain with the same Young modulus. And this is very, very interesting because as you see now, the linear elastic region is a little bit greater than before. So in some way, because this mechanical treatment you have applied to the material, you have improved or you have amplified a little bit the elastic region of your material. The important thing to recognize is that this value epsilon p in here is a permanent deformation because when you unload it, your bar, and you have no loads, you didn't come back to the original coordinates 0 in this case. What you will notice is that you have a permanent deformation that is called epsilon p usually because it's permanent, but this p can represent as well that this deformation is because plastic deformation. So this deformation that has been produced from the point 2 to this point where we started the unloading, there were some some plastic deformation, and this plastic deformation is this value in here. So part of the deformation of this structure was plastic and part was elastic. Because at this point, for example, if you see in this horizontal line that unites the end of this arrow in blue and the axis in here of reference of stresses, you will see that you can decompose the plastic deformation is one value and the elastic deformation that is recordable, you can recover, is this value here. You can see it as well in this graph. If you have a vertical line from this end in the green arrow to the axis of a strain, this value here will be the elastic recoverable deformation, and this epsilon p will be the plastic deformation that is permanent, of course. What happens if you, in your experiment, you load again? So you are here now because what we have done, let's recap. We have loaded the structure until here. We have unloaded the structure till here. If we now reload one more time, in the first place, we are going to have this elastic regime again. Now is amplified. So we are going to follow this path until this point, the point where we have unloaded before. And if we continue, of course, we are going to continue with this plastic behavior we have studied before. And after that, we are going to have a hardening process. Let's say we reach this value of stresses in our experiments and we decide to unload to see what is going on, what's happened. So what we find is, again, that if we unload, we are going to follow a path that is parallel to the previous one, parallel to the original one. So we are going to see that we are going to create a new elastic regime, which is even greater than the previous one, and of course, greater than the first one. So all this mechanical treatment we have producing the material has produced an improvement in the elastic region. And we're going to unload the material, the steel sample, and we're going to notice that the permanent deformation of the permanent strain we have is even greater than before. So basically, when we reach the plastification point or the limit of elasticity at 2 and we continue loading, we are applying a sort of mechanical treatment to the material. We are changing internally the molecules and atoms and the redistribution of the crystals of this material. And we are producing something which is useful for us because this material is stronger than before in the way that it's not exactly stronger, but let's say the elastic region is bigger. So this is good because we like to have structures that act elastically because we don't want to see permanent deformations. We are okay with the small elastic deformation, but we want to recover deformation when the loads are removed. But the cost we are paying for this amplification or this boosting of this elastic region is the permanent deformation we got in this material. So the original length L0 of our wire will be different now. So it's not going to be L0 anymore. It's going to be a little bit bigger. But we have gained this, a bigger region of elasticity.
Anyone else here?
No, I
I'm
think
back
it's
again. Sorry, I had another connection issue in here, but I'm back. So if we continue loading from this point, we will follow the elastic path, and after we are going to have this hardening and the softening, and we are going to break the bark. So basically, what you see is we have transformed this material that at the beginning show, this weird behavior during the plastification process in a material that start elastic, and suddenly, instead of having a plastification, what you have is a hardening and a softening. And this is the difference basically between a ductile material and a brittle material. So if you load and unload a bar, you basically are producing, or you are applying to the material a mechanical process that transforms this ductile material in a brittle material. Because the last behavior from this point in here, elastic, hardening, and softening, is typically the behavior of a brittle material. The shorter this last region, the more brittle is the material. And we are going to see the difference in here. So this is the way we define ductility and brittle materials. So when you have a brittle material, this is the behavior. So you start linear elastic, you suddenly lose the linearity, and you break the material very, very quickly when the material is brittle. So when you have a ductile material, you have a linear elastic behavior first, you have a kind of plastification process in here, hardening, softening, and this, let's say this region is bigger. So a way of measuring the ductility of a material is to measure the area under the curve. The bigger is the area, as in this case, the more ductile is your material. The smaller is the area under the curve, the more brittle will be your material. And if you want to see how this is shown in a real experiment, for example, when you have a brittle material, and an example of brittle material will be a glass, for example. So when you pull the bar and you break the bar, you don't see any neck. So because this, and one important thing to understand and to remember is that the brittle material fail without any warning. So you will be pulling this bar, you will be not noticing anything in terms of deformation, production of necks or something like that, and suddenly you will hear something like clank, and the material is broken, and you didn't have any warning that allow you to identify how danger or how close is the failure of the material. When you have a ductile material, for example, you will see far before the break, the formation of this neck. So in some way, you have a visual warning of being very close to failure. And this is a big advantage in civil engineering, because if you have just brittle materials everywhere, you won't have the opportunity to react against an event of failure. But if you have ductile material, you will see the formation first, and you will have the time to do something about. So, for example, this is something extremely useful, and it was a revolution in civil engineering when we started using reinforced concrete, because the concrete it's a brittle material. So is a material that failed suddenly without any warning because it's not ducted at all. But when you add steel as a reinforcement in the concrete and you create this reinforced concrete, the metal we use is usually ductile steel in order to give our new material, the reinforced concrete, this ductility and this ability to tell us that the failure will come because there are already big deformations. All of this allowed us to construct, for example, buildings made by reinforced concrete, and we can see deformation that are a warning for failure. So this is a good thing for us. And it's a good thing for us in tunnels as well, where we see deformation before the failure. And all of that allowed us to have monitoring on these structures. So today, because sensors are very cheap and very simple to install, and very simple to monitor with electronic devices or with computers, we can monitor now the structures, and this is the tendency in structural engineering these days. So you add to your structures sensors where you can identify vibrations, movements, deformations. So you will have a system that warning you about possible or potential failures far before the failure itself. And this is very, very useful because you can reinforce the structure and you can prevent and you can save a lot of life and money, avoiding these sudden failures, basically. But the thing is, this experiment we have been discussing even which is very simple. So you have only a tensile test in a small bar of steel that's subject to the sample to uniaxial stresses, uniaxial forces. This is a unidimensional experiment. But as you know, reality is not unidimensional. Reality is three-dimensional. So we'll need to run more complex experiments to understand better the materials. And things will be a little bit more complex in 3 dimensions and in 2 dimensions, of course. And this is the reason that we need to recognize that this experiment gives us a lot of information, but it's not the only experiment we are going to do. Because if we think in a 3-dimensional solid, for example, let's say, I will say this small element, you can think in this element as something very, very small because it's a differential element. In an element of any structure, let's say it's a dam or a soil or a beam or a wall or whatever you want to imagine, is we take these small elements inside the material that is that constitute our structure. You will see that every element with this shape, as this small cube, will have axial stresses sigma in the 3 dimensions, in the 3 direction of the space, and you will have 6 different components for your shear stresses. The stresses these stresses, these axial stresses and the shear stresses are the stresses we are going to study. And they are produced basically by the bending moments, the axial stresses, by the shear forces, the shear stresses. But if you see in general these elements in the 3-dimensional space, you see that you have 9 components of these stresses that you need to know if you want to do an structural analysis. Of course, this in the Euclidean space, you will have these deformations and these strains as well. So you will have, I put in here only in 2 dimensions to simplify the explanation, but this will be in 3 directions. So you will have 3 displacements produced by axial stresses, U, V, and W usually are called. And you will have 3 different rotations produced by, no rotations, these are distortions because the rotation produced by moments that will be acting around this axis X, Y, and Z. So the deformations of this 3-dimensional structure will be more complex. And even if we focus the attention on the elastic region, the elastic regime of the material where we recover all the deformations, and by the way, this is the area where civil engineers works. The majority of the time, we work actually in the plastics region with more complex structure, but in general, we try to keep our structure in the elastic region because we don't want to see any permanent deformation. But even if we keep our attention in this simple region, the relationship between the stresses and strains in the three-dimensional world is much more complex than in the unidimensional world. Fortunately for you, in this module, you won't use these expressions and the expression you can see in the screen, but when you go farther in your career, you will have to use expression, more complex expression like this one, for example, that instead of having a Young modulus, and that's it, you will have to have the Young modulus, the Poisson ratio, and you will need an expression in matrix form, because as we are going to study in the second semester, forces in one direction produce deformation in that direction. For example, this sigma x will produce deformation in the x direction, but will produce as well deformation in the perpendicular directions, because the Poisson effects is called. We are going to study in more details in the second semester, but the thing is, these component of stresses are not independent. So sigma x will depend on the deformation in x, y, and z. Sigma y will depend on the deformation in x, y, and z. And the same thing will happen with the shear stresses. This shear stress will depend on the distortion in 3 dimensions, in 3 directions in the three-dimensional worlds, and not just in the corresponding distortion as can be seen in this matricial expression.